Okay, so while we are waiting for more people to trickle in, hopefully, thanks for coming. Um, any questions on material from yesterday? I'm going to kind of recap some of it, but just in case if there's any specific stuff you want me to go over again. Everyone understood everything? Okay, so I can take it easy then. Let's see. So again, just to kill some time, no class on Monday. Obviously, it's a holiday, but no class on Wednesday either. But on Tuesday there is another makeup, and which is in room 2444 or something, whatever I sent out in Piazza. So again, same floor of Walter Hall. I think it's probably on that side of the building. Tomorrow, the TAs are going to go over the material we are doing. So I'm going to walk you through some of the methods that we talked about, min term, max term, Karnaugh maps, cube structures, and also they'll go through some practice problems. I'll also be sending out the first problem set, hopefully by tomorrow, end of the day, maybe Saturday. So keep an eye on that. Conceptual problems, all of them basically. And then the first design assignment looking forward, so it will be handed out sometime towards the end of next week, and it will be on combinational design. So you'll be designing some combinational system using Logisim. So that's kind of the plan. So picking up what we were talking about towards the end of yesterday's lecture. So basic problem that sort of we looked at yesterday was how can we create implementations of combinational logic that are low cost. And in particular, we are limiting ourselves to implementations which are of the form sum of products. So basically, I have terms which are AND terms, and then we are going to take their or the dual of that where product of sums, that is, I have a bunch of terms which are OR terms, and then we are going to AND them together. And a special case of these are the so-called two normal forms, the disjunctive and the conjunctive normal forms. The key thing in those were that min terms and max terms consist of all the inputs, either input symbols occurring. Except what we saw was that there is an opportunity that we can kind of combine them together. And the first approach that we saw was that if we think of each input to correspond to a dimension, and then we have this kind of a binary hypercube, and then we can mark those vertices where the function takes the value 1. And if two vertices are connected to each other by an edge, then we can merge them together. We generalize it. If I have, like in this particular example, this face where all the four corners, the function was taking the value 1, then I can combine them into a face, and more generally, kind of a higher dimensional cube could be structured. And on Piazza, one of the students kind of talked about, could we do 5-dimensional, could we do more dimensional? And indeed, you can. It's just that we are limited by our ability to visualize. Kind of things become very messy very rapidly, but for a software, it's software programs can navigate through high dimensional spaces very easily. When it comes to human design, the approach that I had introduced towards the end was that instead of thinking in terms of these cubes, we think in terms of these stylized tables that we structure, and which you can think of like our cubes which have been flattened out on a piece of paper. And the particular example we have is that is for a 4-input function, so which corresponds to what we have on the left-hand side. And what we do is, since a 4-input function takes 16 possible input patterns, so we have we construct this grid which has 16 boxes. Each box corresponds to a particular min term, or equivalently, box corresponds to a particular input pattern. So if we see out here, the box at the very top is labeled 0. That corresponds to the input pattern 0, 0, 0, 0. Next one is labeled 1, corresponds to the input pattern 0, 0, 0, 1. And obviously implied in this is that we are thinking of our inputs in a particular order. The order we are thinking is DCBA. So when we say 0, 0, 0, 1, that means D and C are 0, 0, and B and A are 0, 1. And that you can see by how we have labeled things at the top. So at the top of each column, it indicates what value B and A are taking. So first column corresponds to B and A being 0, 0. Next one, B and A 0, 1, 1, 1, 1, 0. And likewise, the rows corresponds to DC taking the value 0, 0. Here, DC taking the value 0, 1, 1, 1, and 1, 0. Then to further assist in kind of visualization, what we do is we mark those columns through this kind of thing where we say A and then have this bar, which is basically saying that these two columns, column number, the second and the third column, correspond to whenever A is equal to 1. And you can check that this is 0, 1 here and 1, 1 out here. And likewise out here we draw B for the last two columns, which basically says last two columns correspond to when B takes a value 1. And by implication, first two columns correspond to when B has a value 0, and the first column and the last column correspond to when A takes the value 0. And it's the same thing we do for the rows. Middle two rows correspond to when C corresponds to 1, and the final two rows corresponds to when D takes the value 1. So these are just visual aids that we do it. The main property that this Karnaugh map or the structure has is that neighboring cells, so whether you go to your left or right or top or bottom, and we do this left, right, top, bottom by wrapping around. So, the cell above this cell labeled 1 is the cell at the very bottom, which is 9. So the main property is neighboring cells, horizontal neighbors or vertical neighbors, differ in only one bit. And that we can check for any one of these. So going from 1, so cell number 1 corresponds to 0, 0, 0, 1, and cell number 9 corresponds to 1, 0, 0, 1. So the very first bit, namely the D, changed out here. So each cell you can verify has that property, and which essentially is another way of saying is that these cells correspond to neighboring vertices in our hypercube. Okay, they're connected by an edge. Furthermore, cells which form a 2 by 2 grid or cells which form a 1 by 4 grid, they belong to the same face in the hypercube, and you can check that as well. So for example, if I look at this vertical row, this column, we see it consists of 1, 5, 13, and 9. So 1 is this one out here. So that's 1. 5 is the one out here, 5. 13 is out here, and 9 is at the very bottom. So it corresponds to this face which I'm tracing out here. Okay, so that's the face which goes into the D dimension, and you can verify this thing. So you take any group of 4 cells which either which are either in the same row, same column, or form a 2 by 2 structure. They will correspond to a face in my hypercube. So what this suggests is that I can work in this table and merging edges, merging two vertices across the edge means left neighbor or right neighbor or top neighbor or bottom neighbor, and merging a face means that I look for these patterns like the one we have out here, 1, 1, 1, 1. So this belongs to the same face, for example. So whatever I could do on the left hand side, I could do it out here also. Now, of course, this goes only so far because so we have 4-dimensional out here. In the book, they have discussion on 5-dimensional where you actually take 4 of these Karnaugh maps, the way I have drawn, kind of. So your 5th variable E, you will have. Sorry, you'll have two of these, and then you can go for 6-1, where we'll have 4 of these Karnaugh maps. And that's pretty much where things end. I had given a URL on Piazza where they talk about these 5 and 6 variable Karnaugh maps also. I do not expect you to know them, but again, if kind of some of you seem to be interested in going beyond the class, you can kind of check them out. But pretty much 6 variables is where Karnaugh Map approach kind of maxes out, and we don't go beyond that. So the idea then becomes, given a function, given a truth table, you are going to fill them in this way. It's possible that your inputs may not be called A, B, C, D, but maybe something else. But you may have to pick a particular order. I could take this very same function, and instead of drawing the Karnaugh map where I have D, C, B, A, maybe I will have, I don't know, C, D, and A, B out here, in which case the Karnaugh map will just look different, but it's really the same mathematical function still. Whatever you could do with one ordering, you will have something equivalent with the other. So you pick an ordering, draw the Karnaugh map, and then we go through the same strategy that we were doing with the cubes, namely coalescing minterms. Coalesce, in this case, we are going to coalesce edges and faces, but work in this space. So last time around I had hand-drawn some stuff, but I'm going to walk you through some of the slides. So one thing you really do need to mentally kind of just be very comfortable and remember is that how the structure is, like see how the pattern goes 0, 0, 0, 1, 1, 1, 1, 0, and likewise 0, 0, 0, 1, 1, 1, 1, 0. Only one bit changing at a time. That's very important. So you should have that kind of memorized. This just makes the point that things differ by only one bit. So in our particular function, which is this 1 or prime function, the things which are in red represent those minterms where the function was taking the value 1. So that and everywhere else the function would have the value 0. So in terms of minterms, I can think of them this way, that these particular input patterns, the one in red, correspond to the one where the function was high. And now I can begin to coalesce things. So for example, one strategy could be that I can combine the 2 out there, I can combine the 2 out here. So I have 2 edges, and then what we have now, so if you look at originally, I had 0, 0, 1, 1 and 0, 0, 1, 0. When I combine, the last one, A, disappears, so it becomes 0, 0, 1, X. So similar to what we were doing with the cubes, and likewise the vertical one. Now staring at this, obviously this is not the best strategy, as we kind of saw last time, because I could have combined 4 of these out here, for example. But let's say we do this. Edges also, we also wrap around, so I can also combine the very top one out here with the very bottom one out here. So that's that could be another combination. I could combine 4 of these. That's another possible way of coalescing things. So by eyeballing this thing, you can kind of begin to see what things can be merged. And for these small examples, I mean, humans tend to be pretty good at it. So that's kind of, so I can form larger and larger implicants. So that's kind of our strategy. So to now throw some more definitions at you. So minterms we saw. So minterms is something which is an AND, bunch of symbols ANDed together, where I have a symbol for each one of the inputs. So that we had seen before. Implicant is an AND term or a product term, which, if it is true, implies the function is true. So for example, so I can merge minterms to form more and more compact implicants. So like, for example, if I had xy and xy prime, then that becomes x. Now, so I can express a function as sum of minterms for all those minterms where the function was taking the value 1. I could combine some of the minterms to obtain compact implicants. Now, there are some additional definitions which become very useful. So one is this concept of prime implicant. Prime implicant is an implicant which cannot be made any larger and still remain an implicant. So for example, if I go back out here, so if you look at this guy, 0xx1, this is a prime implicant, because if I were to make it any larger, so I can try to make a 4 by 4 structure, which would be kind of the whole Karnaugh map, then that doesn't work because there are a lot of places where the function was taking a value 0. So a prime implicant is one where I cannot grow it anymore. I cannot do any further merging and still remain an implicant. That is, still have something where the function would take the value 0. So I cannot remove any more variables out of that implicant. And then there is a concept of essential prime implicant. Essential prime implicant is an implicant which is the only one that includes one of the minterms where the function was 1. One of the minterms of the function. So let's go back out here. So let's look at this one. So let's see, better yet out here. Okay. So if I had merged these two, let's say, okay. So firstly, this is an implicant. Is it a prime implicant? Can I grow it any more without? So any more means can I grow it to, let's say, of size, next size up is size 4. Can I grow it into a size 4? Can I merge it with something else and still remain an implicant? Well, staring at it, I cannot, because if I were to try to merge it to the left 2, these are both zeros, to the right 2, well, this guy is 0. The other dimension I can grow the whole column. Well, unfortunately, I have a 0 out here, or and well, that's pretty much what we have. So none of the strategies work. So this is a prime implicant. Is it an essential prime implicant? So essential prime implicant is one which is the only one which is covering one of the minterms where the function was taking the value 1. So looking at this, do you think this is it an essential prime implicant? Yes, and the reason is that this particular minterm, which corresponds to 1101, is covered by only this particular prime implicant. Okay. On the other hand, let's consider this guy. So I could combine this. This is another prime implicant. And let's see. This is, I could merge this. This is also a prime implicant. I cannot grow it any farther. And then finally, this one was another prime implicant. I cannot grow it any further. So let's consider these. So let's look at this 2 by 2 one. Do you think this 2 by 2 one is essential or not? Yeah, it is, because, for example, this top left is only included by this particular one. What about this guy? It 2 is because this one on the right is only included by this particular prime implicant, and actually this one finally is also a prime, is also essential. But let's consider something. Let's see if I were to, I guess in this example, every prime implicant is essential, so we sort of are not an interesting example from that point of view. Now, the reason it's called essential is that if that prime implicant is the only one covering a minterm, then I have to include it in my final solution. So essential, and that's why it's called essential, because if I remember, I would like to have larger implicants. So prime implicants are good because they are the largest one possible, and essential prime implicants would be required because they are the only one which cover one of the midterms. So I would like to have them. So essential prime implicant are essential in implementing the function. A minterm which is in only one prime implicant is called the distinguished one. So it's just another name for it. Okay. So for example, let's say I have three variables, x, y, and z. Implicant xz includes these two midterms, 101 and 111. Implicant x includes all those four. Implicant x is larger than implicant y, so implicant xy and xz. So stuff that we saw before. Now, staring at this, it kind of suggests us a strategy that the way to minimize a function intuitively is that you find all the prime implicants, make sure to include in your function all the essential prime implicants, and once you have included all the essential ones, then you may still be left over with some minterms which are not covered, but which are covered by more than one prime implicants, and then you will have to pick some additional prime implicants to take care of those. So again, the strategy is that essential ones always are necessary, because an essential prime implicant is covering some minterm for which it is the only one. So I have to include it. So I include all the essential prime implicants. Once I have done that, bunch of my minterms will be taken care of, but there will be some minterms which are still not covered, but they have the property that more than one prime implicant covers them. So now I only need to focus on those remaining prime implicants and identify a subset of them which will take care of all my minterms. So that's kind of the strategy that these software programs use, and that as a human you will also have to use. So going back to our example, we start by making larger and larger implicants so that we end up with the prime implicants. So we create this one. This is just a repeat of what we saw. So this one corresponds to 0xx1. So B and C disappear, so rather C and B disappear. Next one, this purple color, that corresponds to 001x. This one corresponds to x101. So D disappear because D changes. D is 1 on this one and 0 on this one. And then finally, the green colored one, that corresponds to x011. So this is the particular so now what we are left with is these are the set of going back out here, all these implicants are prime, all of them are essential, and therefore all of them are needed in an implementation. Okay, so this problem just this particular case happens to be one where every prime implicant is essential. Going back out here, can you name some of the other implicants? They may not be prime, but they are implicants nevertheless. You can break your square. There are 4 possibilities out there. So each one of them is an implicant, but it's not a prime implicant because the square kind of subsumes them. Okay, so there are 4 other implicants that exist. Moreover, each one of the minterms, the red one, that is also an implicant, right? Again, they are not prime implicants. Let's say hypothetically, let's say 14 was also red in color. Okay, then that cannot be merged with anything else, and so it would be a minterm. It's also an implicant, it's also a prime implicant, and it would also be an essential prime implicant. Okay, so you could have these isolated minterms which cannot be merged with anyone, in which case they are essential prime implicants. But for the specific problem that we had, that wasn't the case. Okay, so once you have this list of implicants, that you have this so we focus on prime implicants, we select all the essential prime implicants and a few of the other remaining prime implicants so that all minterms are covered. In this particular case, these are the 4, and now you have to map them into gates. So essentially for each one of these terms, we are going to have a AND function. So we create an AND function corresponding to them. So let's look at the first entry. It says that 0xx1. So that means that I have to take A as is, and I have to take D in a complemented form. So what we see out here is this gate at the very top, where if you see A is being fed as is, and D is being fed with a negative, with a bubble out there. Next row says 001x. That means D has to be complemented, C has to be complemented, B has to be as is, and I don't need the A, and I need to OR them together. So that's what you see as the second gate from the top. Likewise for the third and fourth row. And then I OR all of them together. Okay. So from Karnaugh maps, you do all this merging. You come up with the minimum set of prime implicants that you need to cover all the minterms where the function was taking the value 1, and then going from here to here, the mapping is very straightforward. And then finally, as I had talked last time around, I can apply De Morgan's theorem, De Morgan's law, by putting a bubble at the output of each AND gate and a bubble at the input of each one of the input of the OR gate. And an OR gate where every input has a bubble, I can convert it into an AND gate with a bubble at the output. So this guy is equivalent to this gate is equivalent to saying, okay, that comes from the De Morgan's law. So if I only give you NAND gates, then you can kind of do it that way. One interesting thing about silicon technology is that the natively available gates are inverters, NAND, and NOR. That's how the transistors work. It turns out, and you'll hopefully see it in some future course if you go into the circuit side of things. So anytime you have to make an AND gate or an OR gate, you have to make it using a NAND gate followed by an inverter or a NOR gate followed by an inverter. So it's good. So it's natural to think in terms of gates which are inverting gates, okay, NAND or NOR, and not in terms of AND and OR, just because that's the way the technology is. But this is something unique to this technology. It could be that some other technology AND is is a direct one. And since there is this characteristic that NAND is the primitive one and AND is made using NAND plus inverter, that means AND is always slower than NAND, OR is always slower than NOR. So if you're thinking of a fast design, it's good to think in terms of only inverting gates, okay, because they will lead to a faster design, again, in kind of the standard silicon technologies that are used there. So let me attempt doing something at this stage. I'm going to run Logisim and show you how you can do all this stuff in Logisim as well. CMOS stands for complementary metal oxide. Okay, so MOS transistors or MOSFETs are a type of complementary metal oxide. Yes, I don't know. Okay, but MOSFETs is a type of transistor, and CMOS means complementary means I take two type of transistors, the so-called N transistor and P transistor, and make gates out of them. So transistors comes in two variety, depending upon whether they are positively doped or negatively doped. That is, are they doped with chemicals which are electron rich or electron deficient? Okay, so and you combine two of them, and that is what leads to this complementary, this characteristic that everything is negated basically. Okay, so as I had mentioned earlier, that Logisim actually does allow for dealing with Karnaugh maps and stuff like that. So if we go to project menu, this is on the Mac, on the Windows, it should be something similar. You go to analyze circuits, okay? And in the analyze circuits, you basically get this kind of a dialog box. Let me pull it down. Okay, and then what we do is we add, we define inputs and outputs to it. So we are okay, I think it's one at a time. So we add input A, we add input B, we add input C, and we add input D. We go to output, we define an output, so let's call it X. Then there are many different ways, there are two different ways I can define my function. I can either define a table or I can give an expression. Okay, and for the expression you'll have to select each one of the thing, and for the table. So let's do our function that we were talking about, 1 or prime. So it's a little laborious out here, but I say this is 0, this I want to be 1 because it's 1 on prime. This also I want to be 1, 3 I want to be 1, next I want to be 0, 5 I want to be 1, 6 I want to be 0, 7 I want to be 1, 8 0, 9 0, 10 0, 11 is 1, 12 is 0, 13 is 1, 14 is 0, 15 is 0. Okay, so now I have fed in my table, and I can now ask it to look at the expression. I can look at the Karnaugh map. Okay, so if you see, the Karnaugh map looks like exactly what we had drawn out here. Okay, so this big 2 by 2 square, which, these two terms merge, these two terms merge, and this purple one shows the merging that we had done before. So, and now you can say, and this one is with sum of products. You can also do product of sums, which we haven't talked about, but let's just try it. So product of sums, it actually will, as we will see in a bit, it actually focuses on elements, cells which are 0, okay? Much like when we had done the max term, we were looking at rows which were 0. So same story out here. But anyway, let's stick with sum of products. And now I can say build circuit, and destination circuit main, it says use 2 input gates only or use NAND gates only. So let's say I want to use NAND gates only, and for the heck of it, let's say I want to say use 2 input gates only. Okay, and I say okay, and are you sure you want to replace the current circuit because it's going to draw in this one? So I say yeah, do it, and it gives me this circuit. Okay, now this one looks a lot more complicated than what I had in the slides because I limited it to use only 2 input gates. Okay, if I had said just use NAND gates, it would have looked like the circuit that I had drawn. So moral story out here is that you can feed in kind of your circuit description, and essentially it is doing this minimization Karnaugh Map stuff for you, and spits out the circuit. Okay, and you can, I mean, it is a lot easier to do than kind of struggling through this thing. In homework, I mean, obviously I have no way of policing, so you can use this thing and replicate the answer, but in the exam you do not have access to this, so it would be really recommended that you learn how to do the Karnaugh Map stuff by hand, because there would, trust me, there will be a question and you would need to do it. So again, while this tool is there for you, in the design assignments, absolutely feel free to use it, but make sure in the problem sets you get comfortable with how to do up to a 4-variable function by hand. Okay. Going back out here, let me also walk you through it also has this entry called get circuit statistics. So you can go in there and it will tell you how many pins it has. Well, it has 5 pins because it has 4 input, 1 output. How many NAND gates it's using? Well, it's using 22 input NAND gates. And then I don't know what the final 2 entries are, but it gives you some other statistics. I guess it's summing the gates and the pins out here. Okay. So in any case, useful tool. Now, by industrial standards, this is a very, LogSM is really a baby tool because it can probably handle maybe, I never stressed it out, but maybe by the time you hit 15, 20 input variables, it will kind of just begin to max out. If at all, it can even go up to that. Whereas commercial strength tools can go into tens of thousands of input variables and still kind of do the stuff. So, but anyway, play with it. Bring your laptop to the discussion section tomorrow, so that as when Paul and Salma cover some of the functions, you try them out and see sort of how things look. Any questions on this LogSM part? Did anyone try it out before the class? No. Play with it. Play with LogSM. It's a tool that you will be using extensively in the class, so become familiar with it. Kind of look at the tutorial manual just to become very familiar with it. Okay, so going back out here. So whatever I kind of described out here, naturally you can do with LogSM. Let's look at some other examples. So some other issues. So sometimes we are given functions where for some input patterns, I don't care about the output. So let's say, for example, I asked you to make a function which takes a decimal digit as an input and indicates whether the output indicates whether that digit was prime or not. Now, a decimal digit would go from 0 through 9, so I need 4 bits for it. And following the typical convention, these will be inputs 0, 0, 0, 0 through 1, 0, 0, 1. And then the input bit patterns corresponding to 10 through 15, we don't care about. So these are the ones which I have marked in this reddish shading. And if you see in the output, I have drawn X. So when you see an X on the output, that means I don't care about the output. Depending upon your convenience, you can make any of these rows to be 0 or any one of these rows to be 1s. So what do you think your strategy would be? Should you take them to be 0, 1, some combination? What would drive that? Whatever is convenient. So could you amplify on that? What does convenient in Karnaugh Map? Not always. So what is our goal in the Karnaugh Map? What do we try to do? We try to coalesce things, right? I mean, we want to create bigger and bigger stuff. So if it helps that making one of these X's to be 1 will let me merge some things, then I would go with that. If it doesn't, then I'll count it as 0, Okay, so your intuition is right. So whatever results in a better coalescing of minterms that is bigger and bigger prime implicants is the one that we should go for. So it gives us kind of a powerful vehicle that if in Karnaugh Map or in our cubes, if some nodes are x, I can count any node marked with x as either 0 or 1, depending upon whatever will result in a more efficient solution, lower number of gates, faster circuit, or more typically, like the way we are approaching it, is bigger prime implicants. So let's try out on this one. So if we were to write this thing, so the notation typically goes is that we say the function is the sum of some minterms. So minterms number 1, 2, 3, 5, 7. And then we also list the don't cares. So we say plus D 10, 11, 12, 13, 14, 15, which is basically saying that these are the minterms where I have the flexibility. I can count them as 0 or 1, and each one of them independently. So I can, for example, count minterm number 10 to have the value 1, but minterm number 11 to have the value 0. Okay, so this 0, 1 decision is taken independently for each one of them. So I draw the Karnaugh map, and this time around in the Karnaugh map, you see a bunch of x's. Okay, so I have x's galore out here, and I have a couple of x's out here. So now, looking at this, I would say, okay, so what should be my strategy out here? So remember, our goal is to combine things into a bigger and bigger prime implicant. Okay, so looking at this, obviously I have my good old sort of the original prime implicant that I wanted, that is still there. Okay, and I really cannot make it any larger, right? I could have tried to do a 2 by 4, but then I have unfortunately a 0 out here. Okay, so that I cannot do. I have this guy, which was also there in the old one. Can I make this one larger? So how would you do it? Any suggestion? Which ones do I make once? 11 and 10. So if I make these things 1, so I can essentially take this guy and these guys, right? That I can merge. And I cannot go any larger. And the other thing to keep in mind is, while I see a row of x's out here, there's no point in merging them because that will just introduce an extra term. Okay, and so I'm going to count them as 0. And likewise, there's no point in merging these 4 because these 2 again I would count as 0. So really 11 and 10, if I count them as 1s, then I essentially have 2 prime implicants, and both of them are essential, so both of them are going to be needed. This one is essential because it's the only one covering these, and the one which we created just now, the bigger one, is essential because it's the only one covering minterm number 2. So, okay, so these ones, there is no point in merging them because if I were to count them as 1, it will create a prime implicant, but that's unnecessary. My better strategy is to count them as 0s so that there is nothing contributed to my output. Yeah, so we are going to consider that x's 12, 13, 15, and 14, these are all 0s. Okay. Whereas these 2 x's, the one in box number 10 and 11, we are going to have them as 1 because that helps them make this prime implicant out here, the one for 2 and 3, to be bigger. Okay, and therefore save on one input. So as we kind of talked about, this kind of just will walk through this. So this one is 0xx1, and this one is x1, x1, but really we have no need for it. I'm just kind of listing them. This one is x01x. This one we will need. This one is xx11, but again we don't need it because it would be already covered, but we are just kind of listing them. So we are listing all the prime implicants, okay, right now. So we have these 4 prime implicants, but only 2 of them, two of them are essential. The one which is cyan colored and the one which is green colored. And when I take these two essential prime implicants, then all my minterms are covered. So I'm done at that stage. So these are the essential ones. And after I'm done with the essential ones, all the boxes which had ones are now covered. So I'm done at that stage. There are no remaining minterms. So basically, I am left with these two, 0xx1 and x01x, which basically means, corresponding to the first one, it is A and not D, and the second one is B and not C. So because C position is a 0, B position is a 1. So this is my function, and I map it to the gates out here. I need 3 2-input NAND gates, basically, and a couple of inverters. Okay. And in terms of cost, recall last time around I said the cost of a gate is proportional to number of inputs it has. Well, more precisely, cost of a NAND gate and cost of a NOR gate is proportional to the number of inputs it has, whereas cost of a AND gate, because I talked about an AND gate is always a NAND followed by an inverter, so cost of an AND gate is going to be the cost of the NAND gate plus 1, because inverter has a cost of 1. So in this particular case, what is the cost? Well, I have two inverters, so it's 2 times 1, plus I have 1, 2, and this is also essentially a NAND gate, so I have 3 NAND gates. Each one of them has a cost of 2 because they have 2 inputs. So this guy has a cost of 6 plus 2, 8. Okay. Likewise, we can talk about the speed of a circuit. Speed would mean if I change an input, how much later the output will change. So if we were to say that a NAND gate has a delay of 1 and inverter has a delay of 1, then the worst case would be I change D and then 3 time units later F will change. If I change C, 3 time units later F will change. If I change A, F will change 2 time units later because it is taking a shorter path, and likewise from B to F there is a shorter delay. So usually you'll be given information from whoever designed these gates, what are the delays of these gates, and you are going to look at all the possible ways you can get from an input to an output and just sum up the delays along the way. Okay. So in this particular case, if I were to tell you that inverter has a delay of 1, NAND gate has a delay of 1, then this circuit in the worst case has a delay of 3. Okay. Some units. Okay. I mean, of course, in real life, you will, instead of being given these things like 1 and you'll be given so many picosecond or so many nanosecond, and you're going to add them together. So there are 2 of these metrics as we have seen. There is area cost and there is the delay which characterize these circuits. So we saw sum of products. What about product of sums? Well, just like when we talked about max terms, where we said for max terms we look at rows where the function takes the value 0. It's the same concept out here, that for product of sums we are going to look at those input values where the truth table is a 0, where the Karnaugh map is a 0, or where my cube vertices of the cube have a value of 0. So let's take an example. Let's say I have this function which is given on the right hand side. It takes the value 0 at row number 13 and 15, as shown out here. So row 13 and row 15 are where I have a 0 function appearing. So this is saying that f is 0 when DCBA is 1111 or when DCBA is 1101. Okay, that's English way of describing this truth table. Or alternatively, we can say says that f is 1 when DCBA is not equal to 00 and DCBA is not equal to 0010, right? So f is 0 when I was in row 13 or 15, f is 1 when I'm neither in row 13 nor in row 15. Okay, so this is again kind of a plain English, equivalent plain English description of what this truth table is. And which is another way of saying is that f is equal to this max term ANDed with this the other max term. Okay, so DCBA not equal to 000 is this is true whenever this term, not A or B, not C or not D, takes on the value 1, right? If so, wherever I had actually, hang on a sec. The first one corresponds to 0, 0, 1, 0, and the second one out here corresponds to 0, 0, 0. So DCBA not equal to 0, 0, 0, 0 means not A or not B or not C or not D, because if any of these A, B, C, D was high, if any of these A, B, C, D took on the value 0, then corresponding negated term would be 1 and the ORing would become 1. Okay, so the second term, max term, corresponds to 0, 0, 0, 0. Good rule of thumb to remember is that wherever I have a 0, I'll have, in case of max term, we'll have a term like this appearing. And likewise, we do it for the other one. And this corresponds to, if you go back to our max term thing, it's basically saying max terms 13 and 15. And we have a product of them. So this we have from, I think I'm messing things up. Am I messing things up out here? F is 0 when DCBA is 1, 1, 1, 1. Or when, which is F is 1 when DCBA is not equal to 0, 0. Yeah. Yeah, this was a typo. Okay, so F is 0 when DCBA is 1, 1, 1, 1, or when DCBA is 1, 1, 0, 1. So that's row 15. So this is row 15, and this is row 13. And which is another way of saying is F is 1 when neither one of these things are true. So not of this, which is the same as DCBA not equal to 1, 1, 1, and DCBA is not equal to 1, 1, 0, 1. And then the second term corresponds to 1, 1, 1, 1, and the first term corresponds to 1, 1, 0, 1. So make a note of this typo. Rest of it is correct. So this is the product of 13 and 15. So if I had simply done product of max term based implementation, looking at a truth table, I would have just written this product of 13 and 15. Now let's look in terms of the Karnaugh map. So our Karnaugh map looks like the way I have shown out there. A whole bunch of ones, but boxes 13 and 15 have a 0 in them. And if I want to focus, if I want to create this product of sum approach, you look at the zeros and you play the same game of combining them into larger and larger max terms this time around. Sorry, combine the max terms into larger and larger stuff. So I'm going to combine this. Since there are only two, I can combine these. So I have 0, 0, merge them together. And this is, in terms of merged entry, we would say that B disappeared because B changed from here to here. So yeah, I have an X for B position. And the other three are going to be listed as 0, 0, and 0 because C and D, C was 1, D was 1, and A was 1. But we are going to write them in negated form out here. Because 1 means negation. So what we really have is an ORing of this form, or not A, or not C, or not D. So again, 13 corresponds to, row 13 corresponds to 1, 1, 0, 1, and row 15 corresponds to 1, 1, 1, 1. Okay, so when I'm merging them together, the one which changed, namely this guy, disappears. I get an X out here, and wherever I have a 1, I need the function in a complemented form, so I'm going to write a 0 here. So that's true for all other entries, 0, 0, X, 0, and OR means I'm going to be ORing them together. So that's what we end up with, not A, or not C, or not D. So this original implementation that would have required 2 max terms now reduces to an implementation where I have a single term like this. Cost of this guy is I need an OR gate with 3 inputs and I need 3 inverters. So its cost is going to be 3 inverters, so let's say 3 units, and then the OR gate, its cost is going to be, it has 3 inputs, so cost is 3 plus 1 because I need an inverter at the output. But looking at this, with De Morgan's, I can convert it into what? Anyone? So an implementation, so if I were to map this guy as is, I have this guy, right? Right, and what I'm saying is I can simplify this thing to, in this particular special case, De Morgan's thing is going to look like this. Okay, so its cost can be further reduced. But generally speaking, it would not be as simple to do this transformation in this case, just because we had 1 term. So whatever we could do with focusing on ones, we can also do it focusing on the zeros. Let's take this very example. So I'm going to just give me a sec. Okay, so I'll take this opportunity to see. So let's say now, if instead of focusing on 0, I was focusing on ones. How would I cover these things? So what would, can anyone suggest as big as possible prime implicants? Remember, we are going to focus on ones. We are going to go back to our sum of products. So which boxes will you combine?
You combine the top half.
Okay, so top half. So I can combine these.
And then the first row and the last row.
Okay. I can you're saying the first row and the last row, so I can combine this and this. I still have 2 remaining. First column and last column. So I can combine this guy and this guy. Let's roll over. So I have 3 prime implicants of size 8. So they correspond to, what do they correspond to? Is it an edge, face, something else? It's a cube. It's a 3D cube, right? So I have 3 3D cubes. A cube, in this particular case, means I have eliminated 3 of the variables, right? So I will be left with a single variable in each case, right? So let's look at the top one. The top one corresponds to what? Yeah, so looking at this out there, top half corresponds to not D. So this is not D. What about this guy, which is combining? So it's not C. And the one which is combining the remaining one is not A. So I end up, so I essentially end up with not A and not B and not C, which is equivalent to what we saw out here. Okay. Let's see. No, it is actually not. Not A, not B, not A, not B, not C. I'm ending them together. Okay. So, am I making some mistake? No. Okay, so this was not A, not C, not D, and in this particular case, not A, this is D. So not A, sorry, I'm totally messing it up. So not D, and so not, okay, and this one is not A. And each one of them is a prime implicant, so it's actually not A or not C or not D, which is the same expression that we got previously out here. Point being that in this case, whichever way we tried, we ended up with the same thing. In general, it won't be like this. Again, it's coincidence in this particular example, but you could approach the problem whichever way and see which one results in a lower cost implementation. If you're using logisim, you can just select sum of product or product of sums and try both. So let's look at another example with product of sum. So this is our decimal prime or 1. So this was its truth table, Karnaugh map. And in this particular case, I'm going to focus on merging the zeros. So focusing on this, what would be the first big way of combining a lot of zeros together? What would you do? So if I were to assume all the don't cares were 1, then I have very limited way of combining things. But remember, I have the flexibility of taking some of the don't cares to be 0. So what would your strategy be? And I want to combine zeros into big things. So can I create something of size 8? That's the first thing to look at. So what would you do? Bottom 2 rows, right? So I'm going to combine the bottom 2 rows. Okay. I still have some zeros remaining. What is the best strategy of covering these 2 zeros? First column. So I'll cover the first column. And then finally, I have this 0 remaining. What is the best strategy of covering this? Yeah, so I combine this guy with this guy out here. Okay, so that would be kind of my best strategy. So I will need 3 OR terms ANDed together in this particular case. One of them will have only 1 variable. The other 2 will have 2 variables each. So that's the strategy that kind of we walk through the next slide. So this term corresponds to basically it's the term D, but positive D, so that we will write as a 0 because it will get negated. So OR of 0 and the other 3 we don't care. Then this term, in this term, A has the value 0, is A bar, so that appears as a 1 out here. C has the value 1, so it would take a negated value out here, and D and B we do not care, so it's OR of x0, x1. And then finally this guy out here, A and B are 0, 0, which means they will appear in a positive form, so it's OR of xx1, 1. And putting all of them together looks like that, and the expression that we end up with is following: A or B is coming from this xx1, 1, not D is coming from this cyan colored one, and A or not C is coming from the green colored one, and then we are ANDing them together. So this gives us a product of sum implementation. Go ahead.
Okay, so why do we this like why do we negate everything we get?
Why do we negate everything? So recall the way max terms were working. In case of max terms, whenever we had a row number, so if I had a row number 1111, that corresponded to the max term, not A, not B, not C, not D. Same thing kind of carries over out here, okay? So even while we are coalescing, it's the same property which holds true basically. And then this notation OR of XX11, it's basically saying I'm ORing A and B, okay? This is saying I'm ORing just D, which is basically just D, and this is saying I'm ORing C complemented with A. So implementation looks like this. Again, you can kind of compute as cost function and stuff like that. Okay. There's an alternate strategy for product of sum, and this goes back to making use of the duality property. So let's say you decide that, I only want to learn one way of manipulating Karnaugh map, working with ones, and that I'm uncomfortable with this. Okay, so what we can do is make use of duality with De Morgan's. Okay, so the basic strategy is the following: take the complement of f. Okay, so in the Karnaugh map, wherever I had 1, it becomes 0. Wherever I had 0, it becomes 1. X remains x. Now do a sum of product of this not f, and then take the complement using De Morgan's to get product of sum. That's kind of the basic strategy, right? Because if I have sum of product, I apply De Morgan's, I'll end up with product of sums. So let's work through this strategy. I had, let's say I have this function that I give you, and here cell number 13, 15, and 9 have a 0 in it. So I could approach this thing by combining the zeros, focus on these zeros, and go with the strategy that I just mentioned, kind of working with ORs and kind of creating the stuff. But let's say all you want to remember is dealing with ones. So I convert this thing into the truth table for so strategy 1 is this: I merge these. This corresponds to OR of 0x10, OR of 00x0, and I will have an implementation corresponding to this. So I'm not going to repeat that. So I'll end up with this implementation. I want to show how we can do the same thing by this other strategy. So I take this one, invert it, I end up with this Karnaugh map. Remember, x remains x. In this example, we don't have any. And now I focus on the ones. So, so I apply merge the ones, 1, 1, x1. I merge these two ones. I end up with 1, x01. I create, I say not f is equal to this product of sums. Sum of products. And then, so I have this implementation. And then I apply De Morgan's to say this term, which is exactly what we had obtained previously. So it's exactly equivalent. You can either deal with merging zeros, or first create the function for complement of f, merge ones, come up with an implementation, apply De Morgan's to go back to product of sums. They're both equivalent, whichever makes you work, makes sort of more intuition to you. Okay. Let's try another example. So let's say I give you a 3-input function, which is minterms number 1 and 7, and I want you to express it in product of sums form. So now I'm taking this opportunity to also show you how you can work with a 3-input Karnaugh map. Okay, it's just a special case. 2 of the rows are missing. So I write it like this: CBA. The bottom row corresponds to C. The first row corresponds to C bar. So I fill it in. Let's see. I'll just jump. Okay. So it is minterms number 1 and 7. So this is 0, 0, 0, 1. So this minterm number 1, and this is 1, 1, 1. So this is minterm number 7, and the rest are 0. So this is what this Karnaugh map looks like. Can I merge anything out here? Not really. But if I were focusing on 1, but if I'm focusing on zeros, and product of sums means you should focus on zeros, either that or you should take the complement and then focus on ones. So since we are asking for product of sums, we're going to focus on zeros. So I can clearly merge a lot of zeros out here. I can do this merging first in the last column. What do you think this will correspond to? So if I were to write as an OR, what would we write out here? So how many variables would it have? Like how many variables matter in this one? Which ones are the X? Is C constant across this? Is it? If it's constant, what's the value? Is it just A? Yes, it is just, or it will be just A. Okay, so that's right. And the reason it is just A is the following. So firstly, spanning both the rows. So C is changing. So C doesn't matter, right? Whether C is 0 or 1, I have to accommodate both. So C is X. What about B? Well, B is changing too, because B is 0 in this column, 1 in this column. So B is changing, so that is also X. But A appears as a 0. But remember, we are doing product of sums, so it will appear in a non-complemented form. So this is what this guy corresponds to, or XX1, which is basically just A. Okay. What else can we combine? So we still have a couple of zeros left over. So I can combine this, these two. In terms of our OR notation, what would this be? So C is appearing as a 0. It's in the 0 row of C. So it would actually be C. Okay, so it would be a 1. What about B? B is 1. So that B means it is 0 out here. So it would be not B. And A is remaining, A is changing. So that's an X. Final one. By the way, I just realized that I'm using kind of a weirdo notation out here. So I would write it as OR of XX1. And I'm going to write this guy as OR of 10X. Okay, next one, this one. So anyone, someone help me out? What would this look like? OR of what? C is 0 because it's sitting in the row for C equal to 1. So C will appear complemented. B is 1 and A is X. So it's OR of 0, 1, X. Again, I think on the next slide I probably messed things up. So this would be OR of 1, 0, X. So that's what we end up with. Again, to follow my notation, OR of 1, 0, X, OR of X, X1, and this is OR of 0, 1, X. And then we have to basically AND these terms together. So that would be our implementation. So our implementation is ORing the ending this with this term with this term. So 3 terms. Okay. So that's it. You could achieve same result by inverting the Karnaugh map, focusing on the ones. So now we'll have a lot of ones, and then kind of working with that. Questions on this? So you need to become very comfortable with this. And again, Paul and Salma are going to walk you through some additional examples tomorrow. But I really urge you to try out and then use Logisim to cross-check your work. Okay, I mean, Logisim basically gives you the Karnaugh Map, shows you what it looks like, see whether sort of you end up with similar results. Now, bear in mind that for some cases, it may be possible that there are more than one answers of equally good best cost. Okay, some examples that may be the case as well. For these small examples, we do expect that you will end up with the best result. Okay, of course, if the example was very big, then it's not humanly possible. And even CAD tools and design tools that I mentioned, they also try to find good answers, but they do not make promises that they will end up with the best answer, because for large problems, that's extremely, there are no efficient ways of finding. Okay, so next thing I wanted to cover was that sometimes there may be reasons why we may deviate from this thing about, remember how I said that all I care about is that every box, every minterm should be covered by one of the prime implicates. Okay, it may be covered by more than one, but as long as it's covered by one, we were happy. But there are sometimes we actually do seek to cover them by more than one prime implicant, and the reason has to do with that in the absence of doing that, there may be some weird errors may happen. So the notion is the following. Let's say I give you a combinational logic and I apply some input to it, and it will have some output. And then I change the input. What behavior would you reasonably expect on the output? After some time, output should change to the new value, whatever is the value corresponding to the input. But what if the output misbehaved? So let's say the output was supposed to stay at 0. So for old input value, the output was 0. For the new input value, the output was 0. But what if, because of during this change, it went to 1 for a tiny bit of time? So there's a sort of spike which appears on the output. It was 0, teeny bit of time, it went to 1, came back to 0. So it's 0, 0, but with the spike. So these kind of errors can happen in real circuits that, or for example, the output was supposed to change from 0 to 1, but when you look at it, it will go from 0 to 1, come back to 0 again, and then go back to 1 and become stable. So there could be these kind of transitions that may happen at the output which are not good. And that happens because real gates have delays in them, as we kind of talked about, that OR gate, NAND gate, and all of them, when we change their input value, the output value changes after some time. And there are occasions on which weird interactions between these delays can lead to the output having these kind of glitchy behavior. And we would like to avoid it. So I want to show you how it can happen. Okay, so consider that I have a implementation of this particular function, which is kind of shown out here, 1, 1, 1, 1 in these boxes, the other 4 boxes being zeros, and I have 3 inputs, A, B, C, one output. And let's say I were to look at A and B and C as shown out here. So this kind of picture is called a timing diagram. Okay, these are called so this is referred to as timing diagram. But what is going on is that the x-axis is time. So you see is t equal to 0 here, some t equal to 1, let's say t equal to 1 nanosecond, and then time goes on. So time is moving from left to right, and I'm showing the status of signals A, B, C, and F. So what you see out here is A remains at 1 throughout, B remains at 1 throughout, C goes from 1 to 0 at time equal to 1. What would you expect F to happen? So when A is 1, B is 1, and C is 1, what is the value of F? So f should remain 1 because that's box number 7. And when a is 1, b is 1, c is 0, it is this box 3, so f is still supposed to be 1. So what you would reasonably expect on this figure is that f remains 1 throughout, right? That would be kind of the behavior that you would expect this box to have in an ideal sense. But now let's look at it, what might happen in a real implementation of this box. So in real life circuits, those glitches that I was referring to are called hazards, and the reason they happen is the following. So let's see how might I implement this circuit. So I may combine these two ones, and that corresponds to B and not C. I may combine these two, and that refers to A and C. And therefore, I may have an implementation like this. So I've created two prime implicants. Both of them are essential. I combine them together. I have this particular circuit. Now, looking at this, what is if you see one thing, that the signal C, its effect reaches F from two different paths. One is which goes through inverter, the bottom AND gate, and the OR gate. But then C also affects the output by going through the top AND gate and then the OR gate. So in the bottom case, it is going through an inverter, an AND gate, and an OR gate. In the top case, it is going through AND gate and OR gate. So as you might reasonably expect, the effect of C on the output will take longer time through the bottom path and take a shorter time through the top path. Agreed? Right? So I mean, it's very reasonable to expect that the two AND gates will have the same delay, will take the same time. So C through the top gate and the top AND gate and then the OR gate will take a shorter time than effect of C, which goes through the inverter followed by the bottom AND gate and then the OR gate. So let's say the delays were like this. Let's say the inverter had a delay of 3 nanoseconds. Let's say the AND gate have a delay of 1 nanosecond, and let's say the OR gate has a delay of 1 nanosecond. And just purely by way of example. So now what might happen? Well, let's call the output of this inverter to be Cn, C negated. And at t equal to 1, C changed values from 1 to 0. So when C changed value from 1 to 0 at time t equal to 1, let's look at what happens to these inner signals, Cn, D, and E. D and E are the output of these two AND gates. So if C changes at t equal to 1, when do you think Cn will change? 3 time units later, so it will change at t equal to 4. When do you think D will change? So remember, A is 1, so whatever change happens in C will appear, so it will affect output 1 time unit later. Okay, so C causes a change in Cn at t equal to 4, and change in C also causes a change in D at t equal to 3. Sorry, at t equal to 2. Agreed, everyone? Right? So delay of AND gate is 1. Okay. Now if Cn changes, and remember B stays at 1, so if B stays at 1, whatever is the effect of Cn will cause a change in E. And meanwhile, the change of D will cause a change in F. So this change in D that happened at t equal to 2, and meanwhile E has a value of 0. So when this guy changes, F will be affected at time 1 time unit later, that means at time t equal to 3. And meanwhile, Cn will cause E to change. So the effect that is going to happen is the following. This change in Cn causes E to change at t equal to 5. And meanwhile, F changes twice. Once when D changes, and then it goes back when E changes. So if you see out here now, F does not remain stable at 1 throughout. It goes down to 0 at t equal to 3, and then flips back up at t equal to 6 back to 1, and then stays at 1. So we had expected that f would remain at 1, but what is happening is because of this circuit delays, for a period of 3 time units, it's actually going down. So an observer at the output who would have expected that, all that happened as C changed from 1 to 0, and both before and after, I would have expected f to remain 1, but really what is happening is 1 goes down for a tiny bit of time, comes back to 1. Okay, so do you think it matters? Depends on what you're doing with it, right? I mean, remember we talked about in the very first lecture that there are these circuits where we look at the edges of transitions in the signal, the so-called clock signals and all. So there are circuits where these changes in signal value may trigger some subsequent action, and that can result in some incorrect things happening. I mean, it could be that this transition causes, I don't know, a furnace to turn on or a robot arm to move or some other potentially dangerous thing happening. So, so depending upon your application, this little glitch or spike in the output value may or may not be acceptable. And if it is not acceptable, you have to kind of cope with it. In any case, what this is called is a hazard in the circuit. And the reason is a race condition, as it is called. What is happening is there is a race happening between the effect of C coming to F through two or more different paths. So in general, an input may affect the output through more than one pathway through the circuit, and it may propagate along these different pathways at different speeds, and therefore the effect may affect the output multiple times before it stabilizes, and that can cause these hazardous situations which may be bad for the health of your system. Any questions on this one? This is kind of a tricky example because we are certainly throwing at you that things have delays and the signal changes are propagating at some speed, but that's how the real circuits are. Okay, previously we were just thinking of AND gates, OR gates as kind of mathematical idealization, but in reality these are physical things which are going to take some amount of time. So questions on this one, why this sort of glitches happening? What do you think might happen if C were to change back from 0 to 1? Do you think a glitch will still happen? Remember, C goes back from 0 to 1, output should still remain at 1. What about a glitch? Do you think that will happen? Anyone? I would like you to work it out, okay? So see if this is, okay. Now, let's talk about something else. What can I do to prevent this glitch? So let's say the glitch is bad. I don't want it to appear at the output. I want the observer at the output to see a perfectly solid F remains at 1. Make the paths equal in delay. So that's one possibility. So what I could do is I can put something in this out here which also has a delay of 3. Obviously, I cannot put an inverter. It has to be something which is an identity function, but should have a delay of 3. Right? So I could do that. The problem is it's very hard to make circuits which have identical delays. Okay, it's basically impossible to do it. Okay, because you're manufacturing something, they'll always have some tiny variations in the way they are made, so their delays are going to differ, and therefore the effect will creep in. So it's very hard to predict, make circuits which have very predictable delays. So I cannot do that. But there are potentially other things that we could do, and one strategy, and the reason I mention is works the following. That remember what is happening was I was jumping from this prime implicant to the other prime implicant, right? When C was changing, I was basically, instead of A and C being active, I was going to B and not C being active, right? So the problem that I had was I was changing from one to the other. What if, as C is changing, there was some prime implicant which continued to remain true? So it will hold the output stable. So what I could do is to add this term also, A and B. right? So remember, previously I said you should only have enough prime implicants so that all the minterms are covered. But now we are saying, let's go ahead and introduce this A and B also, even though it is not needed from a logic perspective. But the advantage is both A and B were high, so A and B will remain high. And therefore, this new green term will keep my output F to be stable. And C can change, and nothing bad will happen out there. So I will add this redundant term, okay, out there, and therefore my circuit will look like this. And this particular circuit will not suffer from the hazard that we talk about. Obviously, there is a disadvantage. I'm spending more gates, more power consumption, more dollars, but I have eliminated that hazard. So the reason I kind of brought this thing up was that real life circuits are not the simplistic story of let's just minimize the gates. Okay, there are all these other considerations that come in, and how reliable, safely your circuit is operating is an important consideration. And at times what that means is that we deliberately use more gates if it results in a safer circuit. And this is an example where we end up having a safer circuit by throwing in this extra prime implicant out there. Okay, so any questions on this example? Okay, I mean, this is kind of meant more as kind of a deviation from kind of the standard story that why we don't just blindly kind of minimize the gates. Okay, so summarize basic strategy, manual strategy of doing things. Write K-map, find all the prime implicants, take all the essential prime implicants, and then of the remaining prime implicants, choose enough of them so that all the minterms where the function was 1 were covered. If we were working with product of sums, then you will focus on zeros. Either that, or you will take the complement of the function and then apply this strategy and then do De Morgan's at the end. K-map is rather painful for more than 4 variables. You could do for 5 and 6, but 6 is pretty much the tops. After that, it becomes really very painful. The algorithms behind this, so very early on, back in 60s, there was an algorithm called Quine-Mccleskey algorithm, a Quine-Mccleskey method which was developed to handle larger number of variables, computer algorithm for it. Except even that was too slow by the time we started having bigger chips. So then in 80s and 90s, a lot of research happened, and now we have techniques, like I said, which can go into thousands of variables and handle them like pretty rapidly. So tools are very good at this stage. In real life, tools do this for you anyway. So while if I was teaching this class in, I don't know, 5-10 years ago, and if you were unlucky to have some different instructor, they might make you go through 6-7 variable type functions. I won't. So you need only up to 4. Feel free to use Logisim. In the exams, you will not get, I will not ask you to do with this kind of optimization with more than 4 variables. Hazards can be eliminated by introducing these extra terms so that when the inputs jump from one prime implicant to another one, you introduce a redundant one so that you still have some prime implicant which remain true. So that's kind of the basic strategy. The cube-based approach is equivalent to the Karnaugh Map based approach, but it's the cube-based approach which is what a lot of the logic synthesis software think of these problems in terms of. Next up in the course, so what we have done is we have looked at these circuits where you can take any mathematical function, design this stuff, and like I said, with CAD tools, you can handle arbitrary stuff. But oftentimes, the other strategy which we use in engineering is that instead of designing an entire system from scratch, we rely on others to design highly optimized pieces of my system. I buy it from them and I put them together. So like, for example, if you're a car manufacturer, it's not like you design each and every GM doesn't design each and every part of their cars from scratch. They buy some stuff from different vendors, entire subsystems, and then they put together the subsystems. And it's the same story in kind of Apple doesn't design the hard drives themselves. They buy the hard drives from others. They do not design the processors. They buy them from Intel, and so on and so forth. So in engineering, one of the ways we make designing more efficient, and both in terms of cost and performance, is to let others design sub-pieces. It's the same story in digital systems. That is, one way of designing more complicated pieces of logic is to design highly optimized, often reused pieces. So like, for example, maybe I use adders a lot. So design an adder once and then use it various places in your design. Or if I need a comparator a lot, let someone design a comparator and then kind of use it again and again. So there are these well-used mathematical functions which we encounter a lot. As you might suspect, things like multiplication, division, trigonometric functions, a lot of these things are very commonly used. So the strategy is then to make these basic blocks and then use these blocks to make more complicated combinational systems. Turns out to be a lot more efficient than always designing from from scratch. So the next module, again the makeup lecture on Tuesday, we are going to look into that strategy. We're going to look at some of the very commonly used building blocks, how they are designed, and people have spent years optimizing the design of these building blocks. And then you can design, then as a designer of more complicated things, you can really kind of say, okay, I need an adder, let me kind of use an n-bit adder. I need a comparator, let me use a comparator. So you design your system in terms of these pre-built blocks. Let me show you in LogicSim, if you were to go and look at LogicSim out here, you would see in LogicSim they have like these arithmetic blocks. So you see like it has adder, subtractor, a bunch of divider and stuff like that. It has these things called plexers, multiplexer, demultiplexer, decoders. So we'll see what some of these things are, how they are designed. These are very commonly used building blocks. So very efficient ways of designing them have emerged over the years. Particularly, as you might imagine, like I said, adders and multipliers and all are so commonly used that a lot of effort has gone into creating very fast adders, very fast multipliers, very fast dividers and stuff like that. So we'll talk about those and how you can then kind of use them. So again, as we move deeper into the course, you will move away from kind of now designing in terms of these AND gates and NAND gates and stuff like that to designing in terms of these more complicated blocks. So that's the next thing up. Okay, so I'm going to stop at this stage, and thanks for coming in so late. Hopefully I didn't call you to miss dinner, but we'll see you on Tuesday.